the small questions. But sorry to interrupt, Thomas. Go
Okay,
no
ahead.
No
problem, no problem. Can everybody see the presentation?
Yes, but it's not in presenter mode yet.
Okay, I'll put it in. This should be better, I hope. Okay, I'll go ahead because I think I have.
It's not presenter mode yet.
Not yet.
On top, on the top corner, you have present on Teams. Right corner.
Right corner. And where do I click?
Presenter in Teams, no?
I don't see this. So I'm sorry for the technical issues. Wait, maybe.
Or if not working, we can also share from our end, and then you can just
Still not. No, now it's just going black. I'm really sorry.
If you want me to share, Thomas, I can happily share.
Yeah.
Yeah, that should be better. Okay.
Okay,
I'll
1 second.
close
well,
my
we will
screen.
return to that. So we'll share the screen, and then you can just say when next slide is up.
Perfect.
Okay, thank you very much. This will be easier. I'll start explaining the problem. Why are we doing this research? Well, firstly, this is caused pretty much by the nitrogen mineralization kinetics of animal manure, which are unpredictable, and therefore the legislator has imposed a legal constraint on the amount you can use. Of course, there are crops that need more nitrogen. So what happens is farmers apply their 170 kilos of animal manure, nitrogen from animal manure, and then they use mineral top dressings. But in Flanders, we have too much animal manure, which means it needs to be processed. This is costly, and this is bad for the environment. On top, mineral nitrogen fertilizer is used to produce it. It is bad for the environment, and it costs also money. So a very good solution should be that we process this animal manure so that we have a product which has a predictable nitrogen and other elements, mineralization kinetics. As up to today, there are still legal constraints. We cannot use this, use all these products yet on top of the 170 kilograms of nitrogen allowed. And therefore, a thorough evaluation of both agricultural value and environmental impact of these processed animal products originating from processed animal manure is requested by the legislator. And we're trying to do a small part of that. In the next slide, I will give you a short overview of this one of the products we evaluated in our field. 5 recycling-derived fertilizers were evaluated. The first one is ammonium nitrate, which comes from a scrubbing installation. Ammonium sulfate, which originates from an air scrubber. Pig urine is separated in special stables. Liquid fraction comes from digestate separation, and digestate itself was also tested. On the next slide, I will give you a short overview of the trial setup. It was a really big trial with 23 objects. The first 2 objects were references receiving no nitrogen at all. Object 1 receives nothing. No mineral fertilizers, no nitrogen, no phosphorus, no potassium, nothing. The second object receives no nitrogen, but these objects do receive mineral phosphorus, potassium, and sulfur. And then we come to the positive references. So the objects with which we want to compare the recycling-derived fertilizers. We have 3 objects where mineral fertilizer was applied, 3 objects where pig slurry was applied, and each of these objects was applied in 3 different doses. So we apply the nitrogen fertilizer advice, we apply the advice minus 40%, and we apply the advice minus 60%. We do the same thing for pig slurry. of course, and then we do the same thing for all the 5 recycling-derived fertilizers I mentioned on the previous slide. What we also did is we made sure that nitrogen was the limiting element for phosphorus, potassium, and sulfur. We made sure that there was always a slight overdose available for the plant, so that if there was any yield reduction, it should be caused by nitrogen. So in a nutshell, that was the trial setup. On the next slide, we can see the design. We put also quite some effort in the field trial design. It's a very large field, and that caused the need to minimize or try to minimize random variability linked to soil conditions. We used a number of techniques to minimize, we tried to use a number of techniques to minimize this variability. First of all, it's a randomized block trial. So we repeat everything 4 times. The first 2 references, we even repeat 8 times. It was a split plot design, but most importantly, we did a preliminary, or tried to do a preliminary screening of the field before we installed the trial. This was done in 2019, in the winter of 2018, 2019. The first thing we did was we flew over the field with a drone, taking a NDVI image, which immediately identifies plots of spots on the field which are divergent. We also divided the field in 39 different sectors, and these sectors they were analyzed. We took a sample and we did a chemical analysis. This was done, of course, together with Ghent University. And also we measured penetration resistance in those fields. And based upon all these results, we omitted the sectors that were most divergent from the trial design, and also we put together blocks with similar characteristics. Once we had the field trial design, we could start on the next slide with trial installation. This was done using a field trial injector. So it's basically a large injector which is used in practice, but much smaller and much more maneuverable. So we could install 100 plots on one field without having to drive over every plot several times. Also important to mention is that immediately after injecting every product, we passed over it over every small plot with a spit mill and a heavy roll using a light tractor, which does not create too much compaction. And this was done to prevent first desiccation and also to prevent volatilization of ammonia from the products. On the next slide, please. Here you can see the timeline. It's a 3-year trial. The first year we have sown silage maize. This was done after plowing. The second year we have sown spinach. And due to technical issues, we had to perform non-inversing soil tillage because spinach is a short crop with a rather small seed. And if we, with our equipment, we can only apply the manure of the products before plowing or before deep tillage. So if we would have plowed, all the products to a depth of about 15 centimeters. And then the spinach would never have been able to reach the nitrogen that was applied. In 2021, again, plowing was done as deep tillage, and the crop was early potatoes. On the next slide, please. You can see the weather. The weather was very decisive in this trial and had a huge impact. Sadly, in 2019, we had a very dry year, a very dry period during summer, right in the vegetative stage of the maize. And I also have to mention we're on a light sandy soil. We chose this field because we have to maneuver a lot on it with the trial fertilizer machine, and we thought, well, due to not causing structural damage to the soil, sandy soil would be better. Sadly, we had 2 dry years during the trial, and that has had its effects on the field trial results. So in 2019, we had a reduced growth and nitrogen uptake in all plots due to drought. 2020 was the driest spring ever recorded in Flanders yet, but we irrigated during the field trial, so we could save a part of the field. Of course, we're on a sandy soil and a dry circumstances combined with wind and small germinating plants is very bad for can cause wind erosion damage. So we had a quite heterogeneous field. We had to exclude the 4th block from the data because too many plants died because of wind erosion. They were sandblasted. And in 2021, we had a wet season, more wetter than average. And then early potatoes was the crop. There we have partial leaching of the applied nitrogen because we apply everything before plowing, and the nitrogen is already 15 centimeters deep before the trial could even start. So a part of the nitrogen probably leached out. Then on the next slide, I will give you the results. Sorry for the big tables. I did not have time to compile everything. But the most important thing you see here, these are the 2019 results of the crop, is that all the letters are the same. It's all A. So we did not see any significant difference whatsoever due to nitrogen fertilization, which means that water availability was a limiting factor in this field in 2019, which is sadly not the result we wanted to have. The next slide is also a big table, or the results of the soil sampling taken after harvest. Here also, we can see that differences are rather small. There are not even significant differences between the objects applied. I'm looking at the top table now, and the objects where nitrogen was applied and the objects where no nitrogen was applied. There's no significant difference in residual nitrates in the 0 to 90 centimeters layer, and this might look odd, but it's probably also because of the weather. Sample taking was harvest was done had to be done very quickly just before a big rainstorm, and sample taking was done after. And in between sample taking and harvest, there was about 2 weeks time, and in this period, almost 100 liters of rainfall fell. So we had a dry season, and then immediately it changed to wet and it leached out a part of the nitrogen. Sadly, this makes us not able to identify any differences in 2019. The next slide are the 2020 results. There, as I told already, we had a sandstorm, and as you can see on the picture, the red blocks, or the 4th block of the 4th parallel of the trial, and you can see that there the crop stand is clearly worse than in the rest of the field. This was also significant when analyzing the data. So we decided to leave out the data from block 4 and analyze the data from block 1 to 3. As you then look at the data in the table, you can see basically 3 blocks of results. First of all, you have the block where no fertilizers nitrogen was applied, so objects 1 and 2. And these objects clearly perform very bad because they had no nitrogen. And then you can see ammonium nitrate, which is intermediate and a lot worse than all the other objects receiving fertilizer, which is odd and which is clearly caused by the product applied, but we cannot identify the reason why this happened. And then the 3rd block are all the other products which performed pretty much the same. These strange results of the ammonium nitrates are quite difficult to explain. We analyzed the product, the pH was normal. Also, there were no large amounts of chlorides or sodium present in the product. So up to now, we don't know yet exactly what might have caused this distress. I do have to mention that this happened in extremely dry conditions in the beginning of the trial. So before we started irrigating, the crop received virtually no rain. I think 5 liters fell over a month or something. Also the product was applied, all products were applied very close to the seed, as I told already, because we had to use non-inverse inversing soil tillage. So this is a strange result from 2020. Then the next slide gives the results from the soil. Here, again, sorry for the big tables. Here we saw interaction between the dose applied and the product applied. So I have to analyze everything separately. But again, we see no big differences for 40% of the advisory dose and no differences between products for 100% of the advisory dose. For 70% of the advisory dose, you can see that there are 2 objects with high nitrate content in the topsoil layer. This is ammonium sulfate and pig urine. But soil sampling is variation on soil sample results always is high. And in a trial where because of this sandstorm, lots of plants fell out. And it is possible that samples were taken on patches where no spinach grew, and then again, and it did not take nitrogen. It did not take up nitrogen as well. Then, so I think, but I'm not 100% sure that this might explain these strange results at the 70% advisory dose. Also, it's very clear that all the nitrogen is still in the topsoil layer, so no leaching has occurred. What is also somewhat conspicuous is that based upon crop nitrogen uptake and the amount of nitrogen applied, we would expect more nitrate in the topsoil layer. So some volatilization may have occurred in the dry circumstances in 2020. Then we had the 2021 field trial on the next slide, which is early potatoes. And that was performed in a wet season. Here we see between products applied, so all products that received nitrogen perform pretty much the same. Certainly there were no significant differences. Of course, where you apply no nitrogen, you have a lower yield. But this trial performed as we expect it would have done. Maybe you can say that the yield is somewhat low because nitrogen leached. Some of the nitrogen leached at the beginning of the trial before the potatoes could catch it. The soil samples are on the next slide. These are the soil samples taken after harvest. On the next slide. Here you can see that residual nitrate, despite having a rather low yield, is still somewhat high, and nitrate is well divided over the entire profile. So a part of the nitrate has leached to the 60-90 layer already, probably some nitrate will have been lost during the trial, but there was no difference. You can see no clear differences between mineral NPK, pig slurry, and the other products. And of course, residual nitrate is lower when you apply no fertilizer compared to the objects where fertilizer were applied. Also, residual nitrate here in the 0 to 90 centimeters is for Flanders is rather high, is higher than the legal limit in November. But I have to say that these samples were taken in August, beginning of August, and after this harvest of the potatoes, a catch crop is sown. So these high nitrate, residual nitrate values, this nitrate was taken up by the catch crop and did not leach out to the soil water. The next slide is general conclusions then. Compared to weather condition, first conclusion is that actually we saw only minor differences between all objects, with exception of this ammonium nitrate, and of course in 2020. But most RDFs performed pretty much the same as pig slurry and as mineral NPK. What we did see was on this sandy soil, of course, that the effect of weather conditions, certainly drought, was a lot larger than the product applied and even the nitrogen dose applied. Also important is that if we want to do this preliminary screening again, we have to insert more parameters that consider the effect of drought, that predict how the plant will behave in dry conditions. So soil water content, something like that in dry conditions. In 2021, ammonium nitrate was applied close to the seeds and in very extremely dry conditions, and that led to a yield reduction in spinach, which we cannot fully explain yet. And also important to say is that up to date, we are not able to apply top dressings with RDFs, which means that everything must be done before plowing. Not to damage the soil structure too much. And in wet years, that means your fertilizer is plowed under to 15-20 centimeters, which can cause in some crops nitrate leaching because a rather large amount is applied before trial installation. So this is basically what I wanted to say. And if there are questions, I think there is a Q&A session at the end of the webinar.
Indeed. At the end, but we can already start putting questions in the chat part, of course. Then we can also pick this up. I also see that Zoltan from Hungary has put a question or multiple questions actually. Yes, you can already check that out as well in parallel. Okay, I would like to invite people to also look at the link. That is a small survey in parallel to the demo presentations, so that you can also, from your perspective, from your region's perspective, your country perspective, indicate to us how usable or transferable things that we are presenting are for your particular region, so that's that we can have a better insight on that. But without further ado, I would like to move to the second presentation, and that is by Jean-Philippe Bernard, who is an agronomist who graduated from the École Nationale Supérieure Agronomique de Rennes. He worked as a project manager at the Permanent Assembly of Chambers of Agriculture, so the Chambre d'Agriculture in France. Since 2017, he is project leader for the innovation office of the Chambers of Agriculture of Charente-Maritime and de Sèvres in La Rochelle, to look for innovative solutions, especially related to fertilization management, nutrient recycling, and soils evaluation. He is also he was a member of the focus group on nutrient recycling of the EIP Agri, in which I was also involved. And of course, he is and Chambre d'Agriculture are also a partner in Nutri2Cycle project as well. Jean-Philippe, I would like you to, you have turned on your camera, I can see you and your colleague. You can have the floor, of course, on discussing the substitution of mineral fertilizers with biological fertilizers to optimize organic carbon storage in soil, as well as the nitrogen and phosphorus cycling with two specific application cases from France. Jean-Philippe, the floor is yours.
Thank you, Eric. I will share my screen. Is it okay?
Yes.
Okay. So, hello everyone. I'm pleased to present you the lighthouse demonstration that the Chamber of Agriculture is driving in Charente-Maritime, thanks to the Nutri2Cycle project. So our demonstration deals with the substitution of the main mineral fertilizers with the biological fertilizers to optimize the elements storage and cycling. So is in the background of the new fertilizers regulation.
I don't see the screen anymore. I'm not sure whether it's only me, but I only.
Yeah, your screen is gone. Shafi.
Yes, it's gone. Sorry. Okay. So in the background of the new fertilizers regulation.
But Jean-Philippe, your screen is gone. Your presentation is gone. So could you reshare, or otherwise Martin could share and like with
Sure.
Thomas. It's either way, so you can choose. But we do not see your presentation.
Try to. C'est parti pourtant. Alors.
Yeah, there we are again.
Okay,
Yes.
sorry. A mistake. Okay. 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 Sorry. So in the background of the new fertilizers regulation, our action concerns the topic of the substitution of mineral fertilizers with bio-based fertilizers. So for this project, we were asked to find two kinds of farm system. One farm system combining livestock with agroforestry, and one based on organic perennial crops. So for us, it was a very opportunity to study with these two examples the recovery of residues or effluents at farm according to the circular economy idea, and to focus on the key points for moving from recycling practices to fertilization practices. The framework of the demonstration is the district of Charente-Maritime in the Nouvelle-Aquitaine, New Aquitania region, which contains 15% of French agricultural land. Okay, you can see with the distribution of land use and of technical guidance of farm, that shows that the crops productions are quite important in the agricultural activity in Charente-Maritime, which explains our interest for the fertilization management. According to a recent study initiated by the French Ministry of Agriculture, we can see that the most of the effluents sources are recycled by agronomic way in direct spreading or after composting. So we can consider that the practices of agronomic recycling are quite common in France, and our challenge is not so much learning the use of organic input for crop production as moving from recycling to fertilization management. So our proposal to organize a demonstration operation with two farms as partner. The first farm, the farm Manico, with goose livestock and arable crops, including an agroforestry plot, and the farm Le Petit Bois, combining organic arable crops and organic vineyard for cognac production. So as advisors of Chamber of Agriculture, our mission is not so much designing technological solutions as working on farmers' behavior and practices. So our purpose is to study the different recyclings at farm, find the good conditions for their optimal use as organic fertilizers. So I have to precise that the effluents on the first farm are slurry and manure, goes slurry and goes solid manure, and the agricultural residue on the second farm is oilseed cake. A few words about the farmers participating to the demonstration as partner. So there are dynamic people interested in innovative solutions and ready to lead projects to improve their activities. You can see some of their innovative characteristics on the farm. And their feedback is very important for us to know the issues we have to fix, especially in the organization of their farm. So if we want them to improve their effluents and in general organic bio-based fertilizers, we have to take into account their feedbacks. So the methodology for our demonstration, it is based on 4 steps. So with the characteristic, sorry. Very sorry. First step, the characterization of the organic residues to recycle. Second, soil characterization before and after the demonstration. Data acquisition during the crop growing with remote sensing, manual sensor, and if possible, digital samples. And we hope to use a modeling tool called STIX and made by INRAE, the French National Agronomic Research Institute, to understand the behavior of residues and the balance sheet of elements. So the first farm in our demonstration work is a farm with the agroforestry plot. So it's a plot for arable crops, and we have different parts. A part with agroforestry in form of edges, you can see on the south, and a part with open field. So we have followed 3 years of use of the 2 kinds of effluents, slurry and solid manure. And we have to explain that the plot was only driven with mineral fertilization until our demonstration. With our demonstration, it was the first time the farmers use slurry and manure on this plot. So our testing device divides the plot in several areas. So we have 2 strips, A and B, with agroforestry and combining mineral and organic inputs during the crop. The C area with agroforestry, but only with mineral input, and the D area as control in open field with mineral input. And you can see on the table the difference of organic input between A and B during the 3 years in 2019, 2020, and 2021. The crops in 2019 was winter wheat and 2 years of corn in 2020 and 2021. Of course, it's not a real experimental test, but our work is based on the organization and the work of the farmers. So we could propose some actions to farmers, but we have to follow their own organization and their own management way of fertilization. So some data and results about effluents. So we can see content in nutrient for slurry and for solid manure. And in the 2 cases, in fact, the content of nutrients are too low to consider these effluents as efficient fertilizers. And the use of these effluents to substitute to conventional fertilizers needs to split important traits. It's not the same than the conventional fertilizers. Someone to notice, it's the evolution of slurry and the manure stocks is very difficult because there is no traceability, in fact. So we have to assess it. Some data on result for about soils, and so we did analysis for each area, and we can see that the element contents are generally quite good. And we can see during the 3 years that the agroforestry has a positive effect on biological indicators. We have studied the nitrogenous fertility of soils with mineralization kinetics, and we have a lot of work to interpret the data, of course, but our first observations show us that the three inputs seems to have increased mineralization potential, but the manure input seems to have a real immobilizing effect on nitrogen in the soil. And we are waiting for more data for sea storage, for carbon storage. Sorry. During the crops development, we use data, remote sensing data to follow regularly the crop development. And our first observation are that there is no depressive, but rather positive effect of the presence of agroforestry. And we have only a little obvious effect of organic inputs in addition to mineral fertilization. You can see 3 maps on for the years 2019, 2020, and 2021 with the different crops, wheat, corn, and corn. For the second farm, Le Petit Bois, we have worked on organic vineyard plot, and in fact, even we worked with innovative and interesting people, we can meet difficulties with their work organization, and so we didn't succeed in, we did not manage in setting up demonstration before 2021. Until now, we have only 1 year of monitoring, and we hope to have a second year with 2022. So we have this design. The plot is divided in 3 areas with spreading of oil cake from the farm. We have proposed to spread compost from market to as control, and we made a mixture with 50 oil cake and 50 compost. So we have some data about oil cake, and we can consider that the oil cake is a real bio-based fertilizers because we have enough contents of element, especially for nitrogen. We have more than 3%, but levels for P and potassium and phosphorus are quite interesting. We have the same trouble to assess the stock of oil cake because there is no traceability. In 2021, we made analysis of grape berries for each of the free spreading areas, and we can see that there is a real efficiency of oil cake compared to a market compost for each of the major elements. So we have from left to right nitrogen content, phosphorus content, and potassium content in the grape berries. Of course, our work is in connection with the farmers and is linked to the farmers' practices. So we try to send regularly feedbacks to farmers to explain our action and we send the results they can use. For example, a map of remote sensing index, and we have video conference to have exchanges with the farmers. In fact, the main bottleneck we can meet in this kind of demonstration is to provide the advice just in time to be useful. It's not always possible because with the innovative tools like remote sensing, we have to build references before sending to farmers. It's not very easy. So after three years of working, we have a first bottom-up feedback. So we noticed that the main challenge to improve the use of organic effluents is in fact the balance between agronomic properties of the effluents, the bio-based fertilizer, and the importance of the fertilization management, the fertilization workshop within the farms organization. And with the two farms, we have two different examples. For the farm Petit Bois, in organic farming, fertilizers are expensive and rare. It's not easy to get them. And our demonstration of agronomic properties was a real opportunity for the farm organization. So farmers began to be very interested in the use of this agricultural residue in their farm. But for the manicotti farmer, as the effluents are not rich enough, and as the fertilization workshop is not so priority compared to the other workshop, like breeding or food transformation, there is no real interest yet for changing their current fertilization practices. And the use of effluent in a recycling way is sufficient for them. But it was before Russian crisis, and the increase by 4 for the fertilization price, of course. So we are going the demonstration work until the end of the project, of course, and we have already met some opportunities to present the project and the result of demonstration. Open days in a farm in November 2019. Presentation with poster to the last conference of the French Committee for Sustainable Fertilization in November 2021. And we made also presentation of the project and the results during the last French NTF workshop in January 2022. But of course, we have still some work to do. And at first, we have to develop a pedagogic approach for carbon storage on agroforestry plot with the manicotti farmers. And we are following a new year of testing oil cake with Petit Bois farm. And we foresee to present project and demonstration results to farmers group in our department during the second half year in 2022. And to introduce, in fact, the setup of the new regulations about fertilizers. Thank you for your patience. Thank you for your listening.
Well, don't need to thank us for our patience. It's very interesting. But thank you for the nice input from the cases in France. I would remind the participants, if you have questions, do put it in the chat already, and the presenters can already have a look. I see that there is a lot of dynamic going on in parallel there. That's good. That's good. We can also pick it up some of these points towards the end in the Q&A session. Now I would like to invite to the floor Miriam Cerillo from IRTA, so that is the Institute of Agri-Food Research and Technology in Spain. She has a PhD in environmental engineering, has been dedicated for 10 years to the optimization of livestock manure treatment systems for nutrient recovery, especially in combination of anaerobic digestion with bioelectrochemical systems, membranes, stripping, and or vacuum evaporation. Today she will be telling us or sharing us information on the demo in Spain on ammonia recovery from raw pig slurry using vacuum evaporation plants. So Miriam, the floor is yours.
Thank you, Eric, for this presentation. I'm going to share. Can you see it? Okay, I'm going to talk about just tell about ammonia recovery from raw pig slurry in a vacuum evaporation field plant. This demo develops a process based on low temperature vacuum evaporation. The main aim is to recover ammonia from livestock manure to obtain a salt that can be used as a fertilizer. This process is called Ammoneva, and there is already a patent in the name of Mr. Roberto Stefano Lagarrigue, both the industrial and the brand one. The pilot plant is placed in the northeast part of Spain, in Catalonia, in a farm belonging to UPB Genetic World SL. You all already know that one of the main problems of livestock manure is its high nutrient content, mainly nitrogen. Here in this project, it's proposed to use low temperature vacuum evaporation to obtain marketable products that can be used as fertilizer and help to close the nitrogen cycle. This process is based on the ammonia equilibrium that you can see here in the slide. We have nitrogen dissolved in livestock manure, mainly in the form of ammonium, here in the left part of the equilibrium, and we want to displace this equilibrium towards the right to ammonia, since it's a gas and it's easier to recover from livestock manure. We can transform ammonium in ammonia mainly by increasing pH, temperature, or both. Besides, when we apply vacuum to an enclosed reactor, boiling point temperature decreases below the normal boiling point, thus reducing energy cost because of lower heating requirements. So we can decrease the operation temperature when we work in vacuum conditions. In this slide, you can see the different, or an aerial view of the plant. You can see the different parts of the system. It's all placed next to the farm, and I will tell you the main components, and then in the flux diagram I will explain the function. We have in the first place the influent pit where all the livestock manure is going to be stored until the treatment. We need also a solid liquid separator. In the third place, we have a pacification pit where the increase of pH is going to be performed. We have an Ammoneva container. I will explain in the next slide the main components inside. It's placed here in this part. And finally, we have the effluent pit where the treated pig slurry is going to be stored. And there you can see the components that are going to be placed inside this 20-feet container along with the system controls. In the first place, we have the evaporator, which is a reactor of 6.4 cubic meters. We need also an acid trap that contains lactic acid to absorb ammonia. And we, of course, need a vacuum pump. Finally, we have a basic trap. This is placed outside the container. Here you can see the process diagram. In the first place, we start with pig slurry that was stored in the influent pit. This pig slurry is directed to the solid liquid separator. And the pig slurry liquid fraction that exits this separator is directed to the covered pit. Here, pH value is going to be modified, increase it up to more or less 11 with calcium hydroxide to increase the pH. In this point, due to this increasing pH, some precipitation of phosphates, mainly apatite, is going to take place. And this apatite can be also recovered and used as a fertilizer. So once we have this liquid fraction in the correct pH, around 11, it's directed to the evaporator. This evaporator works in batches of around 1 ton of liquid fraction of pig slurry, and each batch lasts for 3 to 4 hours. With an operation temperature of 40-45 degrees Celsius and 800 millibars of vacuum. So there, thanks to the low pressure and basic pH value, the ammonia equilibrium that I have explained before is displaced to the second species, to ammonia, which is gas. And then it's easily evaporated at this relatively low temperature. So gases are extracted from the evaporator that contains ammonia, and this ammonia is going to be absorbed in the acid of the acid trap, since we decrease again the pH value, and then the equilibrium displaces again towards ammonium form. Finally, the gases that exit the acid trap are directed to a basic trap in order to minimize atmospheric emissions, especially of hydrogen sulfide. So at the end of each cycle, we obtain a processed livestock manure with lower nitrogen content, and on the other hand, we obtain an ammonium lactate solution that can be used as a fertilizer. Due to the plant simplicity, you have seen that it's easy to place in a 20-feet container, and the complete automation of the process, it is suitable to be placed on farm as an on-farm treatment for decentralized pig slurry management. The plan operation monitoring by IRTA started in November 2020, and in this slide you can see as a result the mass balance for nitrogen up to now. We can see that the treated liquid fractions contains around 55% on average of the nitrogen that we have in the effluent, and 20% of the nitrogen is absorbed as ammonium lactate in the acid trap. For the rest of nitrogen, around 4% is found in the liquid solid fraction. 16% is emitted to the atmosphere as emissions, and we have around 5% of losses. This system is continuously being improved around this time of operation, and there are some changes that are being implemented now. The first one is a change in the specification, in the closed specification pit, because it's going to be replaced by this conical tank, because in this way it's easy to recover the phosphate precipitates that you remember I told that were produced. from the bottom of this tank is easy to recover than from the gasification pit. And a very interesting change, improvement is the combination of this Amoneva system with reverse osmosis to recover a salt concentrate and water as final outputs, in addition to the ammonium solution and the phosphate salts. So in the end, no land is going to be needed for the application of slurry at all. And just to conclude, you have seen that the Amoneva pilot plan allows for the reduction of ammonium content in livestock manure, and its recovery in ammonium lactate form. It's a marketable product that can be sold. Also, phosphate is recovered in the gasification step. And very important, it brings the opportunity to combine with reverse osmosis to avoid the need for land. And that's all. Thank you very much for your attention.
Okay, thank you for this nice overview. I have said it before, people having questions can share in the chat, and we will come back to that during the Q&A session. I would also like to reiterate that Margarita, if you scroll up to in the chat part to the beginning, has shared a link to also with us a very brief survey that you can fill in as the presentations are moving along. Then for our fourth speaker today, I would like to invite Edward Someus to talk a little bit about ABC, or animal bone shards as it is known, for phosphorus recovery, formulated biophosphate trials with two comparative plants, elder and wheat. And Edward is an upcycling engineer with core competences on zero emission pyrolysis processing of unexploited biomass and circular economy recovery of novel bio nutrients, including economic industrial scale-up engineering, agri-biotech formulations, and high added value reuse of innovative biofertilizers. So he specialized for EU policy and law harmonization development for circular economy, green deals, is a research expert for chemically modified substances with specialization on phosphorus recovery, the ABCs with the animal bone char, animal bone oils, and biochar products. Yes, I would like to invite Edward to turn on his camera. Edward, can you hear us?
Just one moment, please.
No problem.
Yeah, I'm here. Yeah, okay. Okay, can you hear me well?
Yes, and we can see the screen as well.
Okay, thank you very much, Eric. Yeah. Well, what we do, we recover economically high nutrient density biophosphates that are compound NPKC formulated. The problem with the phosphorus recovery and the phosphorus materials that the European Union demand on phosphate fertilizers 1.9 million tons of P2O5 per year, from which 1.6 million tons imported. Here we can see a slight distribution of the import, 84%. We can see Russian Federation 20%, but also Syrian Arab Republic 5%, and that is also controlled by the Russians. While when we look at Morocco, Morocco is also changing because they are underway to set up nuclear power stations based on extracted uranium from phosphate rock. Another problem is the low nutrient use efficiency of the rapid solution mineral phosphate fertilizers, because on the field these have a strong tendency to be fixed binded into the calcium content of the soil. And this is how it can happen that in laboratory the soil sample is rich in phosphorus, but in the field conditions, the plants doesn't have a viable phosphorus content. So this is a real challenge. The phosphate rock need to be replaced. It's containing cadmium and uranium. Where the cadmium is, there is the uranium. They are always associated. The European Union regulating the cadmium only. However, a few member states, including Germany, already looking for to define uranium contents in the streams as well. I would like to mention that since 1950, in German agricultural land, in every 1 hectare, 1 kilogram of enriched uranium have been spread by mineral phosphate fertilizations. We can see that 95% of the phosphate fertilizers coming from sedimentary rock, which have a high cadmium content, such as Morocco, and only 5% of global reserves consisting low cadmium igneous rock, and such as in Finland and Russia, where the igneous apatite is geologically 20 milligram per kilo in cadmium. Now, in the new situation, in the new geopolitical situation, the agriculture is under extreme pressure of many issues, and there is an ongoing cumulative disruption on the agri-food sector. The phosphate price already increased, but I would like to remind that in 2008, the phosphate fertilizer prices increased 700% in 1 year. So everything is just a starting point. This almost 100% is just a warm up for the price increase. So this is turbocharging the inflation rates, where the food is having a share 16% of the inflation rate. So therefore, the maintenance of the affordable food prices is a very important issue. What is needed? This current and dramatic crisis confirm that we need to accelerate the transition towards sustainability and also to be prepared, better prepared for the future crisis. So there is a need for this rapid transition. Circular, sustainable, resilient, and fair agri-food systems is needed. Adoption of best practices is very much important, but this is important to highlight that at the end of the day, farmers appreciate primarily the TRL9 full-scale demonstrations on their true value field conditions. And this is what the investment readiness level, also 9, and commercialization readiness level 9 is an important factor, because this is what the market players are most interested in. The European Commission, the 2022-133 issued a very interesting documentation, realizing that there is an ongoing crisis which needs to be rapidly managed. When we look at what we do, basically we target this TRL9, 20,800 tons per year throughput. We talk about boundaries. Then secondary raw material, we recycle the biophosphate and the energy, and we turn back the energy back to the agriculture. In our case, the biophosphate processing plant is integrated with several hectare scale greenhouse operation. And we're making a full cycle where we are utilizing different waste streams, byproduct streams, and formulating nitrogen, phosphorus, potassium, the bone char, which is already having an economically interesting high nutrient density, 35% P2O5. This is very much important, the nutrient density, because if the nutrient density is low, then the application dose is high. If the nutrient density is high, then the application rate is low. So, but if you are using high doses in the fields, then different other new problems may come up. And also not to talk about the cost, because the machine cost, disposal cost, the logistics, and so on. So the high nutrient density is a critically important point of the whole action. The final goal is replace or at least reduce the imported critical raw material phosphate rock and replace with domestic or European Union origin secondary biofertilizers and raw materials, and also to decrease the energy costs, because energy and fertilization both are crisis points. We made two tests. One of them is the winter wheat. Usually we are using not too small plots, 5-6 hectares. This is right dimension, and targeting 200 kilo per hectare and 400 kilo per hectare. And in all cases, we talk about not bone char application directly, but always formulated biophosphate. Not only formulated with nitrogen and potassium, but also combined with other organic materials and microbiological substances. Most importantly, we are specialized on fungus, Trioderma harzianum. If we look at the changes, then the target is 10-20% yield increase, because the yield increase for less cost, this is the point which the farmers are most interested in, while the environmental impacts and so on, these are important, but the farmers don't want to pay for it in the product prices. So this yield increase could be reached very, very, very nicely. Elderberry is other interesting crop, which is common in Central Europe. Also, we talk about 200 kilo and 400 kilo per hectare, and number of treatments have been 4. So so this is what we did. When we look at the yield increase, have been somewhere lower than in the wheat cases, but 5%, 10%, 12% increase, it's a very good number. And from financial point of view, and 10% increase is significantly improving the economical performance of the production. So we also have been treated in the past other type of crops, including tomato, pepper, and also preparing larger scale applications in different countries, most importantly in Italy. So this is what we do. And final message to take home, that the Stone Age didn't end because the world ran out of stones. The chemical fertilizer age will not end because we run out of chemical fertilizers. Yeah, thank you very much. The Nutri2Cycle webpage can be seen here, and also the biophosphate.net also welcome to visit. Thank you very much.
Thank you, and thank you for that nice final note on the Stone Age. But moving on to also keep nicely within time, I would like to invite the fifth speaker for today, coming from the University of Milan, Axel Herrera. He is an agricultural engineer and researcher with widely significant agronomy and informatics experience in competitive industry. He has been working on the Nutri2Cycle project as a formal PhD student, developing his work on environmental assessment of undercurrent agricultural technologies towards circular nutrient management, has a big drive for integrating and applying informatic tools, and his interests include geographic information system, life cycle assessment, precision agriculture, and nutrient recycling. Today he will be telling us a little bit about the demonstration in Italy, or the demonstrator in Italy on pig manure refinery into mineral fertilizers using a combination of techniques which are applicable to manure processing. But the screen has gone. Yes. Okay. Applicable at industrial pig farms. That was the final point. Okay, but the floor is yours, Axel.
Thank you very much for the introduction, Eric, and good morning, everybody. As we know, intensive light production has led to significant challenge. This in the managing and distribution of the surplus of nutrients coming from manure that exceed the capacity of the local crops. Therefore, the allocation of these surpluses is needed in order to reduce or avoid the environmental problems related to the losses of nitrogen and phosphorus in the ecosystem. Although there is practice such as solid-liquid separation that might increase the nitrogen and phosphorus use efficiency and even decrease the impact in the environment, the liquid fraction containing most of the nitrogen, potassium, and phosphorus doesn't guarantee a high recovery efficiency, aside of the large volume that can represent and the highly transportation costs related. Therefore, membrane technologies such as reverse osmosis are seen as one of the possibilities to increase the nutrient use efficiency, besides of the water removal, in this order to reduce the volume and facilitate the allocation of these nutrients where cropland will require it. This becomes even more relevant to the new criteria established by the Renew frame that will open a window to the safe use of materials coming from processed manure in nitrate vulnerable zones, as Eric mentioned in the first session. This demo case under study, it's a full-scale facility located in the province of Bergamo in the north of Italy. The system is called Slurless. This technology follows a plug-and-play approach by being a pre-assembled processed plant and containerized in ship containers of 40 feet. It operates automatically and continuously and requires a small area for the installation. The process follows a series of separation and concentration steps that I will explain as follows. It starts with a first pretreatment step that constitutes a mechanical separation by using a screw press, followed by a vibrating screen that will separate the main solid fractions. Then the liquid fraction coming from the last separator will enter in through the first stage of reverse osmosis using a fouling resistant membrane that retains most of the nutrient content in a concentrate fraction. Then the pre-permeate will follow a second and third stages of reverse osmosis in an extra fouling resistant membrane to produce the main final product that is the permeate. In the study of this system, we sampling the raw slurry and the different intermediate and fractions. That was done in 3 times in 6 months. We sampled the dry matter, total ammonia, major and minor elements, as well as heavy metals. Besides, we have a trial field experiment that it was done to compare the yield productivity of corn by using mineral concentrate compared with the traditional use of urea. This was in the last season of 2021. The results, the permeate that represents the main product and follows the whole sequence process, it contained almost the 48% of the initial global mass treated, and in the general balance, it counts for less than 1% for all the nutrients, with ammonia levels below 10 milligrams, and even for potassium and phosphorus below 2 milligrams. In the case of heavy metals, there were no detected or below 1 milligram per kilogram. In the case of the mineral concentrate as the second largest product, it occupied the 1/3 of the total global mass treated, and it retained most of the global nitrogen in the form of ammonia, counted almost for 91%. At the same time, phosphorus is retained, and potassium more than almost the double, related with the slurry in feed. In the case of the solid fractions, the first solid fraction coming from the screw press was well linked with the initial characteristics of the slurry in feed, and counting for 15% of the global mass, splitting most of the total solids in more or less 75%. That it was linked with the high organic content and as well the phosphorus retained in this fraction. For the second solid fraction coming from the vibrating screen, it holds the second biggest fraction for total solids, and as well for organic nitrogen and phosphorus. Both fractions represent the 19% of the global mass treated. From the results from the field trial experiment for corn, there wasn't difference among the treatments, with a yield production of 12 tons per hectare. Besides, there was no additional requirement of chemical fertilizers to cover the demand of other major nutrients such as phosphorus and potassium, because of the content of the concentrate and the effluent of slurry. In the discussion about the advantage of this technology, in a general view, we can see that the 3 stages of reverse osmosis provide a high quality, recovered clean water, ready to be released safely in the environment. in the case of the both solid fractions, they contain around 84% of the total solids, becoming an important source of organic matter and phosphorus. And in the case of the concentrate, representing the 1/3 of the slowly treated, it has a high content of ammonia in 90% related to the total nitrogen. And if we check other properties related to the renew criteria, it satisfies the level contents of copper and zinc, becoming a potential candidate for the renew frame. Although some of the drawbacks of this technology that several studies have mentioned is the relatively high energy consumption that carries membrane technology. Although this technology requires minor resources, most of them chemicals that are related to the pH adjusting and membrane cleaning. This energy consumption is also a factor that could affect the economic performance and the availability because of the higher prices that it could affect the cost of the mineral concentrate. And last, the membrane fouling that should be accompanied by the prevention and mitigation practice in order to avoid the membrane fouling. This will require a constant monitoring performance and cleaning and pH adjusting, and also a well pre-treatment, suitable treatment before it comes to the membrane filtration process. Thank you very much for the attention. That's all. I try to be short. If you have any questions, you can visit our website or follow us in Twitter. We are planning to organize a guided visit in the June. If anyone is interested, you can send us an email or contact us by the Nutri2Cycle website. Thank you very much.
Indeed, and we will be sharing the presentations and the recording afterwards. That means that if you have questions, you will also be able to see the coordinates of the different speakers, so that you can contact us, of course, afterwards. Then we now have room for Q&A, but first I would like to ask everyone to finalize their surveys as well. So the link was sent by Margarita at the beginning of the webinar, because during the Q&A session we would also like to come back on the results of that, or the preliminary results. We will be asking more people in upcoming weeks, and we also want to draft this into a report towards June to see what of our proposed solutions is transferable and how it is perceived from different sides of Europe. So that is something that you can help us develop. So do try and finalize your survey as we speak, and go through some questions so that we can also give a hint of the initial results towards that, from at least the things that were discussed today. Now, I do see a question from Raju Ahmad about possibilities for slurry from cattle or dairy farm, but I'm not entirely sure whether this question was towards the last presentation for Axel. I would assume so. It was at the end of his presentation, but maybe Raju, you could turn on your microphone and explain whether it was for Axel's presentation or for one of the ones before, like the one from IRTA, for example. Perhaps you could elucidate.
Thank you very much. Actually, just I want to know, they use the pig manure for producing these. So they use only pig manure. So it is possible for cattle manure or dairy farm manure. So that's why some countries, especially for my countries, actually now I am doing my PhD at Queen's University Belfast in UK. But when I completed my course, I went back my home country. So that's why I asked this question, because in my country is available in cattle farm rather than the pig farm. So that's why I asked this question.
Oh, okay. Yes, indeed, the facility, this system, it's able to process, to treat any kind of manure, even cattle or pig manure, any kind of.
Okay. Okay. Thank you very much. Thank you.
You're welcome.
And I see you also had a question related to the presentation by Edward Someus. When I go through the chat, I see you also had a question on what is the basic difference between the bio-based phosphate and P-containing struvite fertilizer. So maybe Edward, you could pick up on that. So what is the difference between the bio-based phosphate and P-containing struvite fertilizer?
Yes. Biophosphate is recovered from animal bones. Animal bone is an calcium phosphate apatite type of mineral, same as mined phosphate. This is why both of them have very high phosphorus content, 35% P2O5. Struvite is extracted from sewage water. This is a magnesium phosphate. The composition is different. The concentration is lower, around maybe 20 to 23%. And also struvite having at least some of the types having different other challenges, such as containing or may contain pharmaceutical residuals, illicit drugs, such as cocaine and amphetamine, and also the organic part may be rather infected. Such issues not coming up on the biophosphate. The struvite is an extraction crystallization process. Biophosphate processing is a high temperature, 850 degrees Celsius pyrolysis processing in material core. So this is the big difference between the two.
Yes, thank you very much. Thank you for your nice answer. Thank you so much.
Thanks indeed for the elucidation on that. In the chat, there are also some other questions. There was, for example, from Belen Morales towards Miriam Cirillo on the IRTA case. But I would like to pick it up, that question as well. It was answered in the chat, but I'm not sure whether it was fully answered. So that's why I'm also bringing it to the floor. So Belen was asking in that process that Miriam presented, have you taken into consideration what happens with the potassium and the pig slurry? In the chat, Miriam, you answered indeed, potassium goes into the liquid and then organic matter in the solid fraction. But I might misinterpret the question by Belen, but I think she also wants to probably know what happens afterwards. So the valorization of those particular things, the organic carbon and the potassium, how that is foreseen.
Did you refer when it's applied to the soil?
Yeah. So the final fate, is that taken into consideration?
Well, yeah, we don't have data about this. We haven't done any experiments regarding the application of these fractions to the soil. It's planned for future projects. I'm sorry, I can't answer.
Okay. Yeah, but for future projects, but I think within the demo, it might be interesting to also indeed highlight that potassium also being, of course, a macronutrient. So it is something to valorize as well, and the organic carbon also. So I think indeed to have the full picture, as it were, for the added value of the demo, it is interesting to also highlight those values.
Yeah, let's see if we can perform some experiments.
Or at least, highlight that. And indeed, it was a good question. I see a lot of questions in the chat. Let me see. I see a question from Yingzi Zhang towards Thomas on trace elements such as cadmium content in spinach. I'm wondering whether and Thomas, you replied to that, but I'm not sure from that reply you gave to Yingzi in the chat whether we have made any comparisons whether the dry conditions had elevated levels of cadmium stimulated or not. Maybe you could reflect on that here, or whether that's something, a point of attention that we could look into afterwards. So Thomas, perhaps you could share or shed your light on this question.
I think we might have cadmium contents, but I don't think we used the analysis we normally use or is normally used for. I'm not 100% up to date with what is used in our lab, which analysis is used. I know there is a limit, a legal limit, but I don't know whether we use the same analysis. So actually, I cannot with 100% certainty tell that the content is more elevated or lower than expected. But we did do a project about cadmium and spinach a few years ago. What we saw there is that elevated cadmium levels are mostly associated with more loamy soils instead of sandy soils. It has to do with the CEC of the soil as well, and also the elevation of cadmium in the leaves is more occurs when the plant, the spinach, has drought stress shortly before harvest. What we have here is the first stage of the field trial. So the first 4 weeks, the small plants are growing in very, very stressful, dry conditions. But then we started irrigating, and from then on, the spinach started producing quite a lot of leaves, a lot of biomass. So you have a dilution effect.
Okay.
Normally, I don't expect the cadmium levels to be that high in this spinach. Also, I know that factories that process the spinach, they have to do auto control. And if they would have, I'm not 100% sure, of course, but if they would have seen something, we would know that the spinach was rejected. So I don't think they might be high, but I don't think they exceeded a critical level. But indeed, it might be interesting to look at the data we have and maybe to see whether we can compare them with other data.
Okay. Well, I must admit I was not aware that drought stress was a driver on cadmium, increased cadmium uptake in spinach. So that's new for me. So that's very interesting. I would also not assume cadmium to be a problem in the fields that were used. That there was no historic cadmium accumulation. In experiments that we did in the past using different types of crops, we do see tendency to have elevated non-essential trace element increases like cadmium in sandy acidic soils which are used to grow vegetables. I have not, less so on loamy soils, and then also in the region that this set of field trials were done. I do not expect either that there was a cadmium problem.
We don't have historical pollution there. That's true. It's more
something for me, it is indeed a nice take-home message, and I was not aware about the response of spinach in the drought conditions to have a higher tendency to uptake. That's something that is interesting to know. Wondering, I see from the very first question when we started the presentation, there was a, let's say, a multiple question from Zoltan. I'm not sure whether those were tackled. Then it might have been also, I think it was for Thomas probably. So you answered this. Yes, I think so. You answered those. Yes, it was related to the amounts used, plot sizes, soil sampling, precision application, but maybe you can go through those answers.
Okay. So the nitrogen amount we apply, of course, for every crop, we make a fertilizer advice. So we take a sample before trial installation. We know how much nitrogen is left in the soil. We make an estimation of mineralization from the soil. And then on top of that, we know, of course, what is the crop uptake, the expected crop uptake. And based upon these parameters, we calculate an advice, nitrogen fertilization advice. So for the maize, the silage maize, 150 kilos of nitrogen was applied. Spinach received 210 kilos of nitrogen, and the potatoes received 140 kilos of nitrogen. The plot sizes were 8 by 6 meters, which is enough for the trial fertilizer machine to apply on the surface to apply uniformly. We need about 7 meters drive-in strip, so the injector starts pumping, and after 7 meters, the dose applied is very uniform with an accuracy of about 0.2 tons per hectare, and we then install plots of 8 by 6 meters. So we go back and forth with the fertilizer machine once. And also interesting to mention is that we drive over every plot only once, just as it would have been in practice. There was a question about soil sampling after organic manure application, but I've always learned that after application of organic manure, you should wait a certain amount of time for everything to become more homogeneous, for nutrients to spread via diffusion. But we take samples before manure application, and then we take a sample at harvest. We did not take a sample immediately after application. In the past, that was done sometimes, but that gives very odd results. You cannot, they don't say anything actually, because heterogeneity and the samples are just not accurate if you do that. That's my experience. And I think food safety, that's no issue because it's industrial processed spinach. So this harvest, it goes to a washer and then it goes to it is boiled. So normally it should not be an issue using manure in industrial processed spinach.
Okay. Thank you for those answers, and indeed, Zoltan, also thanking you via the chat. I see there was also a question by Ravi towards Axel on the lifespan of the reverse osmosis membranes treating liquid fraction of manure. Now, Axel also replied to that. The lifespan was based on 3-year service lifespan. Now, I do have some experience as well on using RO membranes and systems on liquid fractions. And when we were doing experiments, we did observe that, let's say, the technical expectancies were not the ones that we noticed in practice at the demonstration level. So the lifetime of membranes, we needed to replace them substantially faster than what was expected 2-3 years lifespan. So I am curious indeed whether the 3-year lifespan that is expected from the, let's say, the manufacturer is also maintained under the demonstration experience, especially considering that liquid fraction is quite loaded and can lead to reduced life spans when compared, for example, when you would use RO for wastewater cleaning. So do you have some insights on that?
No, Eric. Actually, yeah, I got this data from the manager, from the engineer of the plant, and actually this plant just start to operate at the end of the 2020. So, but yeah, probably you are right. It depends of the cooling problems that it has. One advantage of this plant is that it's full monitored. It has a platform that you can monitor remotely. So it has a cleaning membrane in place that it's automatically. But indeed, it will depend of many factors, the lifespan of the membrane.
And maybe it was in the presentation, but what is the retention percentage? So from the liquid fraction, how much percent water and how much concentrate is produced? Because when that's the first thing to deteriorate. When you have cleaning in place of membranes, the retention percentages go downhill because of the fouling. The pressure builds up and you are producing consistently less and less clean water and more concentrate, and then you need to move towards replacement. So do you have a view on the division? Probably it was in the slides, but do not remember by heart.
Do you mean about the retention in the
Yeah, so for per cube ingoing, how much water is recovered and how much concentrate is produced?
Yeah, the water recovery is 50% in the total, in the full process, and the concentrate just 33%. The retention in the first membrane was around 60-70%.
Okay, those sound indeed like numbers that I was also accustomed to. But it would be interesting because you are indeed having an online monitoring platform there to check back with the manufacturer whether or with the ones following it up operationally, whether they are experiencing reduced lifetime. Because I do remember that in the cases that we followed up, this reduced lifetime had a significant impact on the overall operational expenditure, resulting in, let's say, a tipping point between what was economic feasible and not feasible at that time. Now I'm talking about experiments and at a demo level that were 10 years ago. So of course technology has evolved over that period of time, or it should have evolved over that period of time. But it is good to check up on that. And Rahul's question is also, of course, he's doing research on the overall life cycle analysis, so that's interesting to note such practical observations. Now I see a question from Raju towards general comments. How can we get access to the PowerPoints? Well, Margarita will share, well, not tomorrow because it's a weekend, but next week she will to the participants of this webinar, she will share the presentations and the recording as well. So then you will have access to that. But maybe Margarita, you can also now share the results of the survey if it is available at this stage. Yes, so we will just go briefly through what has been indicated for the 5. So for the first one, we have the field trial experience on using ammonium nitrate, ammonium sulfate from stripping scrubbing, liquid fraction of digestate, pig urine, and pig slurry. So a number of pig slurries, of course, is everywhere. So that was a little bit of a reference to compare against. But the other ones are recovered or recycling derived fertilizers. And the questioning was, of course, more towards those types of products. On the short-term transferability, and this is now across countries. Of course, we have asked you to indicate your specific countries, and we will break down this per region and country in the final report, but now this is, let's say, the compiled response of this group. So we do see that below 50% sees short-term transferability, but slightly above 60% sees mid-term transferability of these products to their regions. I'm wondering, these are, in my opinion, low numbers, which is interesting. It will be good to analyze the regional responses in this. Maybe this is also referring to the fact that we have multiple products being assessed. Maybe some of these products will be more easily transferable to other countries than other products. So that might be some explanation there. But in my honest opinion, I was expecting higher numbers on the transferability potential of such products, especially with the fertilizing product regulation coming into force as of July this year. And of course, discussions also going on renure, meaning recovered nitrogen from manure, and synthetic fertilizer replacements, which is also taking place at the European Commission level. I would expect higher transferability, but it's good to notice. Then similar in France, we had specific cases, and actually it's more or less the same image that we see, that the specific cases for France that were proposed are lower in the short-term transferability perceived that way, and slightly above 50% for the medium-term transferability. Well, we will be looking at the specific responses on what the constraint might be there. So that is also valuable information, for which our thanks. And then maybe you can switch to the next slide. Yes. So the vacuum evaporation field plants, very low, reasonably low short-term transferability, and a little bit above 50% there for the medium term transferability. And that, of course, will reflect on the potential adoption of vacuum evaporation itself on pig manure. How I think there are probably two angles in this. One will be the technical part. How matured and will this be in different regions, and how fast can this be adopted as a technique? But the second part will also be context driven. It might not be relevant or applicable for all regions to have such systems in place. You of course have distinction between manure pressure regions, such as, for example, Catalonia and also, of course, Flanders. But in other context where you have more arable land and less animal production by comparison, such as Eastern European countries, which have a lot of arable land available, then it might be less applicable there. So that, I think, I would read into that, but of course we need to analyze a specific answer that you have given, and as well as some other sources that we will solicit for this. But that's how I would interpret this. Then for the animal bone char, it's roughly the same image as for question 3. Roughly around 37 score for the short term, and just above 50 for medium term transferability. Here as well, I would read into it a distinction between technology readiness throughout the regions, as well as local context. In some regions, we have phosphorus in excess, and we actually have a ban on additional phosphorus fertilization from mineral sources. For example, Flanders being one of those. We have a large amount of our arable land is phosphorus saturated according to phosphorus saturation indices, and there is no topping up of P fertilization on top of animal manure, for example. We do not use synthetic phosphorus fertilizer, and in that sense, of course, new technologies which are replacing rock phosphate derived fertilizers will have no transferability here, because we are not using it by law and legislation. But again, that will be more apparent when we scrutinize on the detailed results. Pig manure refinery, it's actually a similar context to the IRTA situation, where we have also refinery and upgrading and upcycling of mineral fertilizers coming from pig manure. Here as well, we see roughly below 40 score for short term and a little bit above 50 for the midterm. And like I said, also for questions 3 and 4, we need to end the previous questions, but 3 and 4 more specifically are similar to this one. We will have to look into the detailed responses, but I would also think about both a contextual background on lack of transferability, as well as a technological one on readiness level, which might be geographically different. So I think this is then coming to the conclusion of this webinar. We maintained nicely within time in our 2-hour webinar. So do not miss out on our next and last webinar. So that's next Thursday, the 28th, starting again at 10 o'clock. So thank you for joining today, and well, we will keep in touch. Those who have not replied or completed their survey, you can still do so. We will take your results into consideration for the final reporting. So on that note, I would like to thank all speakers and of course the audience for its attention and good dynamics during the discussion. So see you all next week.
Thank you, Eric.
Thank you very much.
Bye bye, Eric.
Bye bye.